Can you hear me? Yeah. Good. Okay. Thanks for the conference organizers. Thanks to the conference organizers for organizing this wonderful meeting. Lots of great conversations with people. One of my favorite conferences to come to. So it's a pleasure to speak to you today about work that's been going on in my group in Waterloo for the past 2 years through the pandemic. We've managed to keep taking data miraculously. And so I want to talk to you about a new research direction in NanoMRI that we've been discovering, angstrom scale nuclear magnetic resonance diffraction. So I'm going to tell you what that is. So some of you may, if you're new to NMR, you may not know what it is. So I will get to that in a minute, but let me just tell you what the goals of this research program are. So the goal, like many of you here, is to do three-dimensional imaging, magnetic resonance imaging on the angstrom scale, right? And we'd like to do this not with single molecules necessarily. It can be in volumes of, let's say, 50 to 100 nanometers, but we'd like to get to angstrom resolution. So how do we do that? So during the past year, during the past decade, actually, we've developed sort of a very unique force-detected magnetic resonance platform that allows us to do very sensitive force detection and combine that with coherent spin control. And the combination of those two things allow you to do some very interesting modalities of detection. And so the particular application of those two capabilities I'm going to talk about today is this thing called NMR diffraction. Okay? And so if we can realize atomic scale NMR diffraction, it gives us a new way to study not only structure of materials, but also quantum transport, which is really interesting. So let me remind you how Fourier transform MRI works. The measurements, when you put a sample into a spectrometer and you measure the transverse magnetization, what you're actually measuring is S of K, where K is this wave vector that's equal to gamma times the gradient in the magnetic field times tau. Now, what are these parameters? Gamma is the spin gyromagnetic ratio. Gradient of B is the gradient of encoding a magnetic field. That can be a rotating field or it can be a static field. And tau is your encoding time. So this is a scattering, so if you're doing X-ray diffraction, you get the same signal, right? You get S of K. And K in that case is the momentum of the light you're using. So if you want to get to high spatial resolution, you want a big K. In NMR, to get to big K, what do you need? You need large gradients or long coherence times. And if you can make K large enough, you can get to the atomic scale, just like you could with X-rays. Okay, so how do you get to, from S of K, how do you get to the sample? Well, all you need to do is a Fourier transform. So the father of magnetic resonance imaging is, or one of the fathers, there are two, is Peter Mansfield. So Sir Peter Mansfield, in his 2003 Nobel Prize lecture, gives this history about how he came to think about MRI imaging. So let me just highlight a couple of excerpts here. Let me read them to you. The idea occurred to me to use line narrowing techniques as a means to effectively remove dipolar interactions. That makes tau long in materials like calcium fluoride, and at the same time impose an external linear gradient on the sample, thus broadening the line shape to reveal the atomic or molecular structure of the sample. The atomic and molecular structure of the sample. He was thinking about using this to actually probe nuclei, okay? But then he goes on to say the residual line width was still too broad using practical external gradients, meaning I can't make tau long enough to resolve atomic structure in a single crystal calcium fluoride. It was clear that we had made our task much too difficult by choosing to work with solids, because in solids, the T2 times are short, right? Because strong dipolar interactions. Thoughts rapidly turned to liquid-like samples where the line narrowing approach would be unnecessary. Thus, the invention of MRI. So in fact, this idea of using NMR to probe nuclear structure or atomic structure came first. And subsequent to that, in 1973, they put out this paper, NMR diffraction in solids, with a question mark. And let me just read that short abstract. A new approach to study the structure of solids in NMR is described. Multiple pulse line narrowing, sequence, and applied magnetic field gradients are used. The theoretical analysis highlights the analogy with X-ray diffraction. Experimental results from a model one-dimensional lattice are presented. Of course, that they show this technique, but sort of on the millimeter scale. So how does NMR diffraction work? What's the basic idea? Well, if I have a so let's consider a one-dimensional periodic system of spins, like you would have in a lattice. If I apply a linear field gradient along that chain and evolve the spins, let's say they, each spin processes at a different frequency because of the field gradient. So you wind a helix, and that helix at some time will unwind itself because the spins will acquire an integer number of 2 pi rotations, right? So they'll rephase. So you form what I call a diffraction echo. So if I look at the expectation value of the z-axis magnetization as a function of the gradient encoding time, there will be a time when all the spins rephase and I get all of that signal back again. Why is that useful? Well, that's useful because if I measure that time, that echo time very precisely, I can have phenomenally high resolution in the structure factor. And I can do that in a chemically specific way. I can go and interrogate different directions and different nuclei separately, thus giving me elemental specificity in my scattering. So there's an important caveat here. I give this example in the context of a spatial modulation of a density. It need not be that. You can have any spatially periodic spin state modulation, like you can have a periodic modulation in the z-axis magnetization, provided that that modulation can be refocused under an evolution under a gradient, you'll also form an echo. This is also very important because it allows you to study correlations. So you can study spin dynamics this way. So let me just give you some numbers. What do you need to probe typical solids? Well, this is also pointed out in the Mansfield and Brunel paper. They said, well, let's take a solid where the nuclei is separated by 3 angstroms. What do I need? And I have hydrogens. What do I need to, what gradient do I need for a typical sort of, millisecond time scales of a coherence time I can get with a line narrowing sequence? I need 10 to the 5th Tesla per meter. And they said, this is ridiculous, it'll never work. Okay, so we can't really probe nuclei this way. Well, it turns out in our platform, we can get millisecond coherence times, and we have 10 to the 5th Tesla per meter gradients. Okay, so we got excited that we can actually realize this, right? So what we're trying to do is to look at nanocrystalline materials, and specifically these nanocrystalline materials. These are protein nanocrystals. So you can crystallize proteins to micron-sized particles or hundreds of nanometer-sized particles. And in fact, there is a lot of work done in free electron lasers where they do diffraction of electron beams from these little crystals, and they can reconstruct the structure with sort of angstrom precision, right? This is now, by now, a big industry. The first paper came out in 2010 on this topic. So we'd like to do this with proteins. Also, we'd like to study, the ability to apply these gradients gives us local control. In addition, with global control, you can do Hamiltonian engineering, you can study spin dynamics, so it opens up a lot of real estate or lots of opportunities for studying quantum dynamics. How do we make measurements? We use silicon nanowires as cantilevers. We attach our sample for the experiments I'm going to talk about. It's an indium phosphide sample. We're looking at the phosphorus atoms in that sample. We attach that indium phosphide nanowire to the side of the silicon nanowire. So so the silicon nanowire acts as a very sensitive mechanical sensor, and we use what we call a CFFGS. It's an acronym that stands for Current Focusing Field Gradient Source. All it is a tiny little constriction in an aluminum film that focuses currents to very high density and allows us to generate time-dependent magnetic fields and field gradients, which we use to detect both spins and also to do NMR control. We can also use those gradients for encoding. We've done some spatial imaging using those gradients, and we use that right now for characterizing our samples. The type of gradients we can generate with the CFFGS is 10 to the 6 Tesla per meter for spin detection. This isn't quite as high as what you can get with a ferromagnet, but it allows us to have very good time control and very, very large V1 fields of up to 450 Gauss. The experiments are done at 4 Kelvin. This is the microscope that we use. And we also make our own silicon nanowires, and we make them in an array form. These are 20 micron long, typically 100 nanometer diameter silicon nanowires. Here are 2 batches that we studied. They have very reproducible characteristics, quality factors of about 60,000. This is 130 nanometer arrays, spin constants of 600 micronewtons per meter, 300 kilohertz, 1 attonewton per root hertz at 4K. This one is slightly softer, has better force sensitivity of 500 zeptonewtons per root hertz. For spin detection, we use a modulation waveform that has where we modulate at the gradient at the frequency of the mechanical oscillator, and then we interrupt with an adiabatic fast passage to invert the spin. This waveform, I'm not going to go through the details. What it does is it gives you a very clean spin signal on resonance. So we measure the z-axis magnetization in these measurement blocks, and then in between we turn off that modulation and we do some NMR encoding. And what you can show is that if I study the correlation between 2 successive measurements, I get the expectation value of the density matrix evolved under whatever unitary I'm applying in the NMR encoding sequence. So the other thing I should say is we study statistical polarization. So the reason why we have to do it this way with this kind of correlation is because the correlations don't live very long. So in the case of phosphorus spins, the correlation time is around 3 seconds, which is pretty long. And these measurement blocks are 1 second. So we make them shorter than the actual correlation time so that we can so that there's something to measure, right? Otherwise, the correlation wouldn't last. The other thing we need is very good unitary control for global control, where we have to apply some NMR sequence. We need global unitaries. We have a very large magnetic field gradient coming from the constriction, so applying hard pulses is not good, right? Because you cannot apply the same unitary to all the spins in your ensemble. So what we came up with are these optimal control theory pulses. They incorporate things like Hamiltonian engineering for zeroing the dipolar revolution during the time of the pulse. They refocus chemical shift Hamiltonian. So they act like a delta function pulse, even though they're like 12 microseconds long. And you can apply these things back to back, and they have very high fidelity. So this is 99% fidelity. This is some data we showed in polystyrene some years ago. They have similar fidelities for the phosphorus data that I'm going to show now. The samples that we use are these indium phosphide nanowires grown by our collaborator Dan Delacoux at Canada National Research Council. We attach them to the tip of the silicon nanowire with a pipette. There's no gluing involved. They just stick by van der Waals forces. And this gives a very, very clean attachment. The quality factor of the oscillator doesn't degrade. This is a characterization we did of the actual sample volume we studied. We applied various kinds of pulses, both Rabi gradients and Larmor gradients. These are these different contours that you see. And you can encode in these 2 different contours. You get a time series. You evolve the pulses in time that you encode with. You Fourier transform to get out the density of spins along these different contours. And then we match them up with the theory for what we expect for that conical tip. This is a 20 nanometer gold catalyst particle. The volume that we study is about 80 nanometers tall. This is about 60 nanometers across at the top here. Okay? We imaged both the proton spins on the surface. that's this. There's about a 2 nanometer layer of water, and the phosphorus spins as well. So let me tell you about indium phosphide, NMR. There are 3 NMR active nuclei. Phosphorus is spin 1/2, 100% abundant. There are indiums, which are quadrupolar, and we decouple those when we make measurements, typically, especially if we're studying spin transport. T2 star is about 70 microseconds. When we decouple with a CPMG sequence, we get out to the T2 time of 270 microseconds. We can apply additional decoupling sequences. We use the symmetric magic echo sequence, and we incorporate those OCT pi halves pulses that we develop in this control sequence. We can extend that 270 microseconds out to about 13 milliseconds. So we have long coherence times and large gradients. We encode in the Raffi field gradient by just asymmetrizing this rotary echo part in the magic echo sequence. That's a detail. I won't bother to get into it, but just suffice it to say, during these times, right, we can encode with the gradient in the Raffi field, the gradient of the Raffi field. And what does those gradient contours look like? This. The Raffi field looks, the constant contours of the Raffi field look like these surfaces that you plot. These are actual calculated contours for this constriction that we use. And these are the actual Raffi frequencies. The Raffi frequencies are these, you'll see this U that I write down. The U coordinate is just the Raffi frequency. And it varies as a function of position. In the volume of the indium phosphide sample, there are essentially these slices that cut through that are parallel to the XY plane in the sample. So this is an actual Raffi frequency distribution measured for the sample that we're going to study. So the Raffi frequencies extend in this range, right? To create the periodic structure, we actually we developed something called a band inversion pulse that allows us to selectively invert part of our Raffi frequency distribution. And what we can do with these pulses, is to create a grating. So essentially a diffraction grating by inverting slices that are 10 kilohertz wide, so they're separated by 20.4 kilohertz. So it makes this sort of striped pattern that you see here. So these are, the red is where the spins are inverted, the yellow is where we don't invert them. So it creates this periodic structure, and what we wanted to do was demonstrate NMR diffraction on the nanometer scale from this structure. So what we do first in our pulse sequence is to encode this periodic structure in the indium phosphide, and then we follow that with a Raffi gradient pulse that then tries to refocus that pattern back to its initial state. So this is the expected pulse. This is the expected signal that we would get from this structure, and this is the echo. This is the diffraction echo that we want to see. And indeed, this is the data that you see on top. We can measure both the in-phase and quadrature part of this diffraction pattern. The NMR diffraction is also phase sensitive, so you can map out both the in-phase and quadrature parts separately. And from the location of the echo, we back out what the pattern we imprinted was. From the fit, we find that it's 20.29 plus or minus 100 kilohertz plus or minus 140 hertz, and that matches well with what we would expect. And so you can ask, well, if that frequency resolution then corresponds to a position resolution, what is the resolution with which you're determining the period, the spatial period of the structure? And it's quite high. So near the tip, we can resolve the period with a precision of 0.2 angstroms. And in the back, 80 nanometers away, because the gradients are lower, the precision is less, it's 0.6 angstroms. You can do one other thing with this kind of technique. You can actually spatially move this chirped pattern. So we shift the frequency by 4.7 kilohertz. So you take that entire sort of spatial modulation and move it in space by, near the tip you move it by 7 angstroms, and in the back you move it back by 1.9 angstroms. So again, you measure the diffraction signal, and notice that you very clearly see the phase shift in the signal because of the spatial shift of this grating. And from that, you can back out the absolute position of the grating in space with a precision of 0.3 angstroms near the tip and 0.8 angstroms in the back. All right. Now, what I've also plotted in these colors is the envelope of these patterns. So if you were measuring something like X-rays, you would be measuring intensity, and all you would have access to is this envelope. You notice you hardly see any shift in the envelope because it's so small. But because this is a phase-sensitive measurement, it clearly shows up in the phase of the modulation. So it allows you to make a very, very sensitive measurement of the absolute position of some spatially periodic structure. And then, of course, you can invert the Fourier transform to get back the spatial patterns in real space. We decided to have some fun with this. So the sample, our silicon nanowire sample chip, is mounted on a small piezo. And so you can physically move the tip relative to the gradient source. So what we did was we applied a voltage to the piezo, and it moved the nanowire by something like an angstrom, okay? And we start from a uniform state, and then we use these SME4 sequences to apply a very, very high pitch. So I don't know if you can see it, but you see this moire pattern. That is because there's a very high spatial periodicity that we've imprinted in the z-axis magnetization. This is the phase of the z-axis magnetization. It has a pitch of 2.1 angstroms. So that means that spins that are 2.1 angstroms apart get a 2 pi rotation near the tip and 5.8 angstroms in the back. So at this location, when the piezo is moved slightly, we encode this very high spatial periodicity. Then we move the piezo to its equilibrium position. We just zero the voltage. So it moves in Z by 1 angstrom. And that takes about 380 microseconds for the piezo to mechanically move. So we apply an SME4 sequence that basically suspends any evolution. So we freeze that pattern and wait for the piezo to get to its equilibrium position. And then we do the inverse unitary. We unwind this pattern that we wound. But we unwind it at its new location, where the fields are slightly different. But you're only 1 angstrom away, okay? And so what you get is an interference pattern between those two fringe patterns that you've imprinted. One at position 1, one at position 2. And this is the residual phase that you expect. So these are all calculated color patterns here. This is the actual data. So you encode and decode with 960 microseconds, so almost a millisecond of encoding. And this is as a function of piezo displacement in the z-axis, this is 1 angstrom. You already see the signal go to 0. This is the modulation envelope that we expect. The different fits that you see are because it's to account for the fact that the piezo moves in both y and z. So the y-axis motion is in fact about 10 times larger than the z-axis motion, but the z-axis gradient is what dominates. It's the strongest gradient. So the grading that you're applying is really in the z direction. And what the y-axis motion does is it changes the visibility of that modulation that you see. The other thing we've done is to basically measure the echo at 2 different locations of the piezo that are, again, separated by about an angstrom. And you can see the shift in the phase of the signal as a result of that 1 angstrom motion. Well, in fact, it's not quite 1 angstrom. It's 0.81 angstroms. And the precision with which you can measure the center of mass of your tip is 7 picometers. Okay? This is just interfering the spin signal. And this is because we can apply such a large wave vector to do this encoding. Okay, so this, I think, opens up a lot of opportunities for studying dynamics, actual physical dynamics of spins in a sample. You can also, and it really demonstrates that, we can study crystal structure this way. The other thing, how much time do I have, by the way? This is sort of the second part of my talk, so I don't know.
You have 5 minutes.
5 minutes. Okay. So the other thing we decided to do was to study spin diffusion. So just spin transport. So all the stuff that I showed is we don't allow for any evolution between the time we encode, create some spatial pattern and detect it. But suppose you put some evolution in there, evolution under some Hamiltonian. So the dipolar Hamiltonian. So we have access, we're operating at 3 Tesla, we have the truncated dipolar Hamiltonian. That Hamiltonian has this flip-flop term, which will make the magnetization move. So what we did was, before we get in there, let me just tell you how this works. On long length scales and long time scales, the dynamics of this flip-flop dynamics obeys the diffusion equation, where this diffusion constant comes from the dipolar couplings in the system. If you apply a sinusoidal modulation in the magnetization, that will decay due to spin diffusion with a power law that goes like e to the minus k squared times the diffusion constant times time. Okay, and so k squared is sort of the hallmark of diffusion. And David Corey in the late 90s used this kind of scattering approach to look at spin diffusion in calcium fluoride, but on the micron scale. So what you do is you encode some helical texture, and then you let it diffuse, and then you unwind it. You do this encoding decoding thing that I showed you, and you see how much signal is left. So we asked the question, what happens if you now go to the atomic length scales? So the way the measurement works is you start out with some uniform state. You use the SME4 sequence to encode some spin texture, some spin helix. So let's say you're rotating the spins around the y-axis here. And then you evolve under the dipolar evolution. But because we have indiums, we have to decouple them during that time. So we apply a CPMG sequence, which decouples all the heteronuclear interactions. And then you do the inverse unitary, and then you look at the correlation between what was the signal in the beginning and the signal at the end. So if you have no evolution here, you expect to recover the whole signal because you just basically unwind that helix and you get back to the initial state. But with diffusion, now things are going to move around and you're not going to come back to the initial state. So what we see in the data is if I apply a long wavelength modulation, there's an initial decay that's a Gaussian. That's just the transverse part of this helix decaying with T2. That has a time constant of about 350 microseconds. Then there's an exponential part. This exponential part is the spin transport due to flip-flop interactions. On long wavelengths, it takes a very long time for it to diffuse. As you crank up the encoding time, you're winding up that helix, and we can wind it up so tight that we can make the nearest neighbor spins alias. So you basically fold over so that the Hamiltonian comes back to its original form. Except we don't have a single tone because there's the wavelength that we're encoding with is not uniform because the gradient is not uniform from the constriction. We actually have a distribution of wave numbers that we're encoding with. So for encoding times of up to about 360 microseconds, this angle is less than the nearest neighbor angle, which is 2 spins separated by 3.4 angstroms, is less than pi. But as you go above that time, it becomes greater than pi, and now your wave vectors get aliased back. Okay? But we decided to do this study, and it's very interesting because the Gaussian part doesn't change, but the exponential part gets shorter and shorter, and it seems to get stuck at around 1 millisecond. We did a very detailed study of this, and you can map out what that exponential time constant is over a large range of encoding time. So the encoding time is essentially a wave vector. It maps onto that. And so for long wavelengths, indeed you see this e to the minus k squared power law. And then it transitions at a wavelength of around 2 nanometers to 1 over tau e rather than 1 over tau e squared. So so it goes like k, 1 over k rather than 1 over k squared. So this is the hallmark of ballistic transport. And to my knowledge, it's the first time this has been seen in a dipolar spin network, okay, in 3D. These are actual calculations, so we decided to calculate using what's called a flip-flop model, essentially a random walk model, where you calculate the couplings using Fermi's golden rule between nearest neighbor spins in this network. We have about 2 million spins in our tip. We take all of those 2 million spins and then calculate and just imprint the grading and then see what happens in the evolution. What's amazing is that the red dots here, this is not a fit. This is just a calculation based on the dipolar couplings. It lies right on top of the data. So it seems to look classical, in fact. Okay? And the blue dots are a calculation using the diffusion equation, where we calculate the diffusion constant from a hydrodynamic model, and then basically put it into COMSOL with finite element analysis of the diffusion equation, with the initial condition being that modulation that we apply in the beginning. And those are the blue dots. And of course, it's the diffusion equation, so it's always diffusive. So it goes like e to the minus k squared, and you can clearly see the deviation from diffusive behavior. And if you want to see more about this, Pritam Priyadarshi has a poster on it. So I guess I'm out of time. We've also looked at things like the XY helix. So this is a helix in the XY plane. And then you can, what you find, in fact, is that in the infinite wavelength limit, you see T2. Essentially, you just tip all your spins into the XY plane, and you measure T2. But if you apply a texture, interestingly, T2, in fact, increases by about 50% for a helical texture. And there's some theory behind that as well that we can talk about later. So the next step for us is to use this kind of device, which I'd be also happy to describe to you, but this generates very uniform magnetic field gradients, and this kind of device is what we want to use to study crystal structure. So in summary, NMRD is a phase-sensitive, chemically selective, non-destructive technique to measure structure of periodic structures on the angstrom scale. NMR could be used to image nanocrystalline materials like protein nanocrystals or synthetic heterostructures with sub-angstrom resolution. And this ability to encode and measure periodic correlations on the angstrom length scale opens new pathways to study many-body spin dynamics in quantum systems. This is the wonderful group of people that I work with, and there's an opening for a postdoc in my group, should any of you be interested. So please talk to me if you are. So thank you for your attention.
Thank you very much. Questions?
Thank you for the nice talk. I had a question. So in your setup, you have both a gradient in the static field and in the Raffi field, right?
Which we can control. If we're encoding with the static field gradient, then we have that.
Because they are both generated by the same constriction, right? But I thought for MRI you don't need a gradient in the Raffi field, and does it now give you some extra possibilities, no. or would it be better to
no, you can do, there's actually a name that I can't remember right now. You can encode with the Raffi field gradient. It's been done. It's just not done in an MRI scanner.
Do you need the gradient in the Raffi field to do this encoding or not?
That's what we use. I mean, we could have used the other one as well. The geometry for us is nice because the Raffi field gradient are these isosurfaces, right, that cut right through the sample and gives us these nice layers, right? The other one is funny. The other one is sort of fans out and cuts through in the other direction. So we want to get away from those nonlinear gradients eventually, where we just have linear gradients in 3 spatial directions.
But I thought the static field was also created by your constriction, right? Or is it
No. We have 3. No, that's from a superconducting magnet.
Ah, okay.
Yeah.
Can I? Okay. So could you explain a little bit more in detail? At some point you show how you do the encoding, but I have to say I didn't quite follow how it works.
Well,
So you have,
fast.
you have this 20 kilohertz spacing between pulses, and
Yeah,
maybe you could just.
I didn't get into the
central idea.
pulses.
Yeah.
I didn't get into the pulses because they're not easy to explain in this kind of talk. The way it's done is you apply a spin lock field, and you go out. We're about to submit a paper onto the archive. It's in the supplements in that paper, but basically what it is you apply a spin lock field, you go off resonance, and you apply a modulated AC field that then tips selectively some portion of those spins that were locked to anti-locked. Okay, and you can do that because you have a Rabi field gradient, so you can select which bandwidth of Rabi frequencies you invert that way. But I don't have time to really get into the details of that sequence. Just take my word for it that, so I showed you, you don't have to take my word for it. You can see the data, right? This is the, sorry. Some of these have some timelines in them. Yeah. So you can see this is 100 kilohertz inversion, where this is the calculated profile that we would expect for what that pulse should do, and it follows very well, right? So this would select this particular range to invert. The reason why we use the reason why we went to this kind of scheme to do it is because it allows us to imprint these modulations anywhere we want. So we can offset the modulation relative to the gradient pulse that we use for interrogating, that we use for the decoding part, right? So we have that initialization, and then we have the readout part. So the relative phase of that can be adjusted through these pulses, which allows us to really see the phase-sensitive part of NMR diffraction. Yeah.
Hey, thanks for the great talk. I think I might have missed it, but what determines the scale where the transport transitions from diffusion to ballistic?
I don't know.
Ah, okay.
That is something that we really need to. So there are two papers that we're putting together. One is on the actual diffraction technique, and the other is on the spin transport part. So the only thing we've done so far are those simulations that I showed. But there's many, there's a lot of many-body physics that goes into trying to understand how that transition happens, and we need to talk to theorists to figure that out.
Okay, with this, let's thank Raffi.